All right. Good afternoon, everyone, and thank you for joining us for today's webinar. Today's webinar is the first webinar of 2018. We are going to be doing a close look at 3D microscopy for firearms identification. Today's presenter is our own Dr. John Morgan. Dr. John Morgan is internationally recognized for his work in forensics, body armor, special operations technology, and predictive policing. He currently directs and develops forensic science research, training, and quality assurance programs, including the National Institute of Justice's Forensics Technology Center of Excellence, who is bringing you today's webinar, and the Substance Abuse and Mental Health Services Administration's National Laboratory Certification Program, or the NLCP. Dr. John Morgan is responsible for management, business development, and strategic planning to maintain and grow our programs in forensic science and related areas of education, policing, homeland security and defense, and international capacity building. Previously, Dr. Morgan was a member of the Maryland House of Delegates and Congressional Science Fellow of the American Physical Society. In 2007, he received the Service to America Medal for his work to improve the nation's capacity to conduct DNA analysis. The Forensic Technology Center of Excellence disclaimer: the opinions, findings, and conclusions or recommendations expressed in this presentation are those of the presenter and do not necessarily reflect those of the Department of Justice. Any products and manufacturers discussed are presented for informational purposes only and do not constitute product approval or endorsement by the U.S. Department of Justice. All right, and without further ado, I'm going to go ahead and switch everyone's layout to our presentation. And Dr. John Morgan, if you'd like to go ahead and take things from here.
Okay, thank you very much, Josh, and hello to everyone across the country. I see some folks from Latin America too, so welcome to those folks. This is a presentation that was actually a much longer one. Robert Thompson from NIST and I were invited by the Forensic Advisory Committee in Arizona to go to Phoenix and give a 4-hour in-person seminar on optical topography and as it relates to firearms identification. That was very well received. So what we're doing here is condensing that set of materials down, hopefully to an hour of worthwhile material for you. We had over 400 registrants, and I see we already have over 200 actual participants in the room. So very much appreciate everybody's enthusiasm and excitement for this area. It's a very, very important one, I think, for the forensic community going forward. I hope you learn a little bit from me here over the next hour. For those of you who want to learn a little bit more in terms of in-depth and what we can get to during this hour, I'm going to tell you about a few resources up front here. And if you see, there's a pod over to the lower left of web links. All of these resources you could get to from that pod. The first one is the landscape study that we published last year on forensic optical topography. That landscape study, like many of our other landscape studies that come out of the Forensic Technology Center of Excellence, is kind of a consumer reports, as it were, looking at all the different options out there from in the commercial side for microscope systems. It also talks about some of the considerations with respect to how you might bring this kind of technology into operations and where the technology is going. So please take a look at and read through and understand that landscape study as part of your as you're interested in this topic. Also, we're upcoming here later on this month. We're having the Impression, Pattern, and Trace Evidence Symposium. The Forensic Technology Center of Excellence sponsors the IPTIS Symposium every other year. We're having it at the Renaissance Hotel in Arlington. You can still do in-person registration, but I also encourage you. This is if you like webinars, this is a great way to actually attend this session. Without using your travel dollars, you can listen to all of the presentations, not the workshops, but all the presentations at the IPTIS Symposium online live. And to register for the conference, use the web link over to the left, and you'll be able to register for the IPTIS 2018 online conference. If you can't make it to DC here later in January, there will be both a workshop, a very in-depth workshop done by Alan Zhang and some of the other folks from NIST, Ryan Lillian and Nick Petrayko, and Eric Smith from the Department of Justice FBI are giving a very in-depth workshop there. That won't be online, but there will be several interesting presentations, including on things like congruent matching and things like that from the NIST folks and other folks. I know Ryan is talking as well, so please take advantage of that material online if you can. So the bottom line here is that when in the 90s, when the IBIS system first was developed by FTI at that time, now Ultra FTI, the ability to image a bullet or casing was much less than what it is today. And so I've given you kind of from a different perspective, what the difference is between what we might have been able to do in imaging 20, 30, 40 years ago and what we can do now. This is actually a comparison of images of Mercury from the Pioneer spacecraft on the left in 1975 and the Messenger spacecraft on the right in 2013. It isn't just that the image is better. It's that what you can see in terms of the detail of the, and if I may say, the topography of Mercury is a very, very different thing going across those 40 years. And the same thing is true here for optical topography as it might be related, or microscopy as it might be related to firearms identification. It's a very, very, very different kind of imaging and information and level of information that you can use. Optical topography is kind of how we've decided to refer to this, at least within the FTCOE, and I know this is the term that NIST prefers as well. Optical topography provides a three-dimensional view of the surface of a bullet or cartridge case at resolutions that capture the full range of subclass and individual characteristics. So, and in this case, of course, we're using optical systems to do it. And we're going to talk a little bit in detail about the several different kinds of ways of approaches that can be done, the different kinds of microscopes that can be used to create, to do optical topography, to do firearms examination, and we'll look at those in detail and some of the pluses and minuses of each of the different approaches, and also some of the companies that are involved in this. And I just showed you, this is just one firing pin impression over to the right here from the NIST website talking about their work in forensic optical topography, and you can see the link there to the NIST work. And I encourage you also to check out what NIST has been doing. They have been working for over a decade now in this area, and the work they've done has been extraordinarily important to the development of this technology. The systems are distinguished by three different things: the collection of three-dimensional data across the surface, the digital image storage and manipulation, so you're not actually using the image processor of your brain, which is an excellent image processor, but using a computer to do the image processing as well to help you with that, and lateral resolution in tens of microns. And that is a very, very, very different from what you might have seen in what is called the Heritage IBIS system from the 1990s. And it's really an amazing advance for all of us and opens up new possibilities operationally. The applications for this are now, first, of course, is to go to the next level for IBIS or NIBIN, and that is to build and search a reference database to find the source of a bullet or cartridge case from the scene. And even that, of course, has been changed an awful lot. I don't think many jurisdictions previously have even attempted to do cold hits of bullets. That is still difficult for a variety of reasons that are fundamental to bullet matching, but is now possible with some of these advanced microscopy tools. Second, as a complement to the comparison microscope for difficult comparisons. So the comparison microscope is still, of course, the tool of choice for the firearms examiner, but these systems can actually be a very nice complement to understanding match or non-match decisions. To supplement the image data taken from the comparison microscope, for example, as well. Fourthly, to clarify the basis on which an examiner makes a comparison decision. So you would be able to illustrate for others a little more easily sometimes what the basis for a comparison decision might be using data from the optical topography microscope. And finally, and this is of course the holy grail, is to make comparison decisions. Particularly the hope is that it will allow us to inform quantitative metrics that are for the basis of comparison decisions. That is, now, of course, the firearms examiner makes a qualitative decision, looking through the comparison microscope and saying, "Hey, I think this is my decision on the comparison." It is potentially the case that the optical topography microscopes and data systems will allow us to look more at making quantitative decisions, or at least putting a statistical metric behind the qualitative decision. So this is actually fairly old technology in some respects. This is the fellow who actually would be the father or grandfather or whatever you want to, Marvin Minsky of optical topography. He invented the confocal microscope all the way back in 1955. And for those of you who are like me and you're fans of the history of science, I encourage you to learn more about Marvin Minsky. He made enormous contributions to artificial intelligence and is the inventor to a large degree, certainly a large contributor to the development of neural networks, to virtual reality. If you've ever seen in the little stores, the little like Spencer Gifts or something like that, you see the little hand that comes out and grabs a coin and then goes back into the toy. That's a class of useless machines. Marvin Minsky invented hundreds of such machines, and including that one, including the little grabber, the coin grabber, and was a consultant on 2001. And of course, we owe him some gratitude for creating the confocal microscope. And as in most things, there are visionary forensic scientists who we also need to remember. One of them, just 3 years later, after Minsky's invention, was thinking about how you might be able to do to look at the topography of the striations on a bullet or cartridge casing. He created something he called the striograph, which was actually a physical stylus that you would look at through a microscope, and the microscope would be used to guide the stylus across the striation. And he actually did comparisons using this method, and he wrote a book that I understand at one time was fairly what was kind of required for new firearms examiners. I suppose it's not anymore. You can still get this on Amazon. Some of the old some old copies of this, An Introduction to Tool Marks, Firearms, and the Striograph. It's good to remember that there are people in forensic science who have really cared a great deal about trying to bring new technology into place. Unfortunately, Davis's idea, because it used a physical stylus and also was extraordinarily time-consuming, was way ahead of its time. In 1958, it just wasn't possible to do this, and to do this effectively, and also do it in a way that we knew was non-destructive. But now, using optical techniques, we can sort of take his vision and make it a reality. So there are many types of microscopes that qualify in this field, and honestly, a full listing of the types of microscopes that can create three-dimensional data would take up several slides, and you probably would still come back if, or I know Ted Vorberger or somebody like that might come back and say, no, John, you forgot one. But here are the four main categories that I think we can worry about here for our purposes within the forensics community for firearms examination. Focus variation, in which the in-focus plane of reflected light is scanned in the Z direction. More simply, you might think of it as if you have a camera where you focus in on a face, and then you might shift the focus just a slightly bit. You might focus in on the ears instead, or on the background, and you could shift the plane of focus backward and forward and build up something that looks like a three-dimensional picture by just looking at that analytically. Confocal microscopy takes that to the next level and actually has pinholes or uses lasers to make sure that the incident and reflected light from the object are always in focus. You're only looking at in-focus instant and reflected light, and as a result, confocal microscopy tends to be one of the most accurate ways to be able to determine what the three-dimensional topography of an object might be. The third one is interferometric-based techniques. For those of you who know about Cadre Forensics, that is an interferometric-based system, but the brass track system is also an interferometric-based technique as well. I'm sorry, photometric stereo is what the gel sight is. In photometric stereo, the amount of light that is reflected from the surface depends on its orientation. So imagine each point on a surface is like a mirror, and if it's higher or lower or oriented in a slightly different angle, then the amount of light is going to change, and photometric stereo relies on that. So those are the four main types of microscope that we're going to be taking a look at. Let's start with confocal microscopy. The picture on the left is one particular system, and it shows you, if you look, and I don't know, Josh, can they see my my cursor looking at that, or do I need to use the draw tool so they can see where the pinhole
you can use the pointer button that's at the very top, and that will follow your mouse around.
Okay.
Just click around the picture, and that will follow your mouse click. There you go.
Yeah, here's what is called the NIPCAL disc. These pinholes, what they do is they control which light that's reflected from the object actually comes back into the detector, and ensures that only in-focus light is coming back into the detector, and therefore that only the light from a particular plane is actually coming back in to make the topographic image. As a result of that, you can imagine, in order to actually build up an entire topographic image, you need to scan across the entire object, and this can take some time. But usually these systems have come a long ways, and you're able to do these within seconds or minutes now. The NIPCAL disc has it's more great history, by the way. That's where the initial motion pictures were done. They used NIPCAL discs back in the late 1800s and early 1900s to show primitive motion pictures. And so when modern confocal microscopy came about, they just sort of borrowed what at that time was 50, 60-year-old technology and used it to build the confocal microscopy systems. The bullet tracks, not the brass tracks, but the bullet tracks uses a confocal microscopy type system, and that's the one from NanoFocus. So yes, and there it is. I showed the picture here in the previous slide, and this is the NanoFocus confocal microscopy system. That's at the heart of the bullet tracks system. And you can see the little cartoon there off to the left about kind of what I mean by the use of the pinholes to keep only the in-focus light reflected back into the image. And the XY resolution of these systems tend to be very, very good. You can see it's either 1.5 or even sub-micron resolution. And the Z resolution here is 10 nanometers. Now, one thing I want you to keep in mind with all of these systems, and that is that there's artifacts in any kind of imaging system that you might choose. There's going to be artifacts in these imaging systems. That is, you really do not know, for example, that the Z data that you're getting is an exact replica of the Z data from the object. It's that there's going to be some differences just from the fact that what you're doing is you're doing a technique, an optical technique in this case, to try to find out what that depth is in the object. And there's going to be some errors associated with that. Some of those are systematic errors. There's going to be some analytical errors. There's going to be errors associated with how you manipulate the data. We'll talk a little bit about that in some detail here so you can get some insight into how that works. But the bottom line here is that there's always going to be, when you do any kind of microscopy system, you're making a representation of the surface, and you have to assume that there's going to be artifacts. Now, there are artifacts associated with comparison microscopy as well. We just don't think about that because they kind of get the experienced examiner learns how to look at surfaces in the comparison microscope. And the human brain, as I mentioned earlier, is an extraordinary image processor. It's the best image processor that we know, and so the brain is very good at sort of, we can say, look past, but understanding and taking account for the problems that you might have in a comparison microscope. Those become explicit when you actually are able to do this kind of work, where you're putting it down into data. You're actually reducing it to real data. And as a result, we need to think more cautiously, more purposefully about those artifacts and take them into account when we do the analysis. So, and I'm going to allow for Ultra FTI to do a little commercial here, because I think that they kind of sum up kind of this picture of what the differences are among the first, second, and third generation of microscopy would be. And I think they do it very, very nicely on some of their materials. And that is, the first generation was 2D imaging and data segmentation based on class characteristics. The systems were mostly standalone, not networked, because it didn't make sense to network when you had the kind of image data that they were producing, and basically included basic image comparison algorithms. Now, the second generation were the higher resolution 2D imaging that you would see in NIBIN around the year 2000 and throughout most of the 2000s. Used more specialized image comparison algorithms, and they were integrated into the NIBIN network and could manage larger databases. Although, let's be frank, both the scientific research and the operational implications were that the interjurisdictional hits were not that common during that period. Again, mostly because of the limitations in the imaging equipment. The third generation introduces the three-dimensional imaging, and in my view, about the same. The comparison algorithms really have not changed that much, at least in the NIBIN system. There are some more advanced algorithmic approaches now coming forward, but the imaging certainly has revolutionized and allowed for interjurisdictional hits. One of the things I think that we don't do as a forensics community enough is we don't sell how great these advances are to the folks who are doing either in the public or detectives or in policing. We don't recognize the operational impact that these changes have. I'm going to talk a little bit about that here in a bit. And again, just to give you some idea of just how I just love the beautiful images. And this is a cross section from Ultra FTI of a land impression from two different bullets. You can see where the here's the, let's see, am I getting it? There it is. And here is the there we are. There is the comparison line between the two. Really, really, really beautiful images, and you can see why these create some compelling matches, and but sometimes too compelling. One of the things that we need to keep in mind is that when we start to do matches, even with cartridge cases, which of course are a little easier, a little more predictable, we can see some score matches that are really, really astounding, and you say, well, gosh, this is definitely a match here. But again, sometimes the brain is too good of an image processor, and we can be fooled. And we can also be fooled by looking at a score and over-interpreting what it is telling us. So for those of you who aren't familiar with him, I recommend the work of Cedric Newman at South Dakota State University, where he has looked at how these scores actually correlate with respect to whether they reflect real matches or not. And the scores are very good tools for working with a reference database, but it's very good to use some care, because you think about it, this data here that we're looking at on the screen is gigabytes worth of image data. And you might reduce that comparison score down to a single number. You're throwing away 99.9% of the information when you go down to that score that comes out of an IBIS workstation or from another system if you use a different system. And as a result, you aren't always, you should rely on it to help guide you as you're doing matches, but you should not rely on it saying, well, if the score is 999 out of 1,000, then that's it. That is simply just not the case, and that's not what Newman's research and is actually telling you. And here's another just beautiful, beautiful set of images from that's from the brass track system there. So the Sensifar actually is a different system. It's used primarily in Europe and around the world. It isn't as common here in the United States, where I'm talking from, but it's actually been used an awful lot in operational crime laboratories. It has a confocal microscopy capability. It has been published by Derek McLaren, now with FBI, then at the time with Alabama State Laboratory, looking at 10 consecutively manufactured 9mm Ruger barrels in one study, examining one land area only. And when I say there's modest overlap that he observed among the barrels, that means that in most cases he was able to distinguish one consecutively manufactured barrel from the next. But there were a couple of instances where there was some uncertainty. But he only looked at one land area when he was doing that particular study. So one might imagine that if he had looked more extensively, he might have been able to distinguish them one from another. And when you're looking at consecutively manufactured Rugers, that's a pretty impressive demonstration. The casework samples demonstrated that the system could distinguish a larger population even with this overlap, and that it was very, very important when you're validating this kind of an instrument to look at the acquisition parameters. That is, if you scan more quickly, the system is going to be making compromises that you may not want it to make with respect to the image quality. And as a result, you know, the classic tension between the efficiency of collection and the quality of data is something that you must keep in mind. One thing that he noticed, and that is that he looked at the subclass carryover and the use of waviness. Now, these are terms of art to some extent. Waviness in general looks at features in the 1/4 millimeter to 8 millimeter range, and the data shows that in his case, they used the confocal microscope. He felt could only be used to exclude matches only. But what he mostly was concerned with is the idea that this waviness was where a lot of the characteristic information may be seen in these barrels, with the speculation that if you can imagine the manufacturing process of a barrel is like any object. It has a certain kind of vibration frequency it likes to hum at, as it were. Derek talked an awful lot about different ways of analyzing this data. And you see the list under workflow here. There's like 8 or 9 different ways that he processed the data. And one of the things that's an outcome here that's very, very, you should keep in mind, is very similar to the score idea. And that is, every time you process data, you're losing information. And so if in the long run here, when you're looking at optical topography data, the use of the raw data in order to do quantitative analysis is the way to go. And when you have, and you want to be very careful about choosing the amount of analysis that you do. As these systems come into practice in the crime laboratories, each individual type of data analysis that is applied, every type of filter, for example, that's applied to the data should be documented and understood, and it should be done in a way that is consistent across the examination of the firearms data. And for more information about Derek's work, I strongly encourage you to look at his one paper in the AFT Journal from 2015. Focus variation is the next one. There are several different kinds, as I show in Alicona, infinite focus off to the right here. Again, if you think about this is just you instead of having these pinholes keep everything in focus as you're looking at the reflected light, instead it pushes the focal plane back and forth across the object, and then analytically using the computer pushes everything back together. Now, there is some controversy about focus variation that it's not true optical topography, because you're using the computer instead of the pinholes to be able to make this three-dimensional picture. Myself, my view is that, again, as I mentioned, there's artifacts in all vertical resolution data and in all horizontal resolution data, for that matter. And therefore, I include focus variation instruments in true optical topography instruments in the family of them, and they have certain advantages. One of them is, as you might imagine, this because the system is a little bit more flexible in terms of the optics. You can have larger working distances. You can use true color. You can look at rough and smooth edges a lot more easily. and you can even turn around an object. That is, you can go around a corner of an object. So it might end up being something that is useful for bullet examination or something like that. And its specifications are comparable to that of a confocal microscope. And in fact, in some respects, the lateral resolutions can be slightly better in some of the commercially available systems. One of the things that I really enjoy, pieces of research I really enjoy in this area, is not in firearms per se, but a different kind of tool mark. Scott Chumbley has looked at Iowa State, has looked at using the Alicona to look at screwdriver impressions, as well as some other tool mark impressions, and to help to provide an objective and statistical variation of verification of the assumption that tool marks are unique to tools. And he has done a variety of very interesting research, and I think has developed it to the point that if there is a laboratory that is looking to do something a little bit more rigorous in these kinds of tool mark examinations, and maybe be a little test case for Dr. Chumbley, I think he would be welcome to that, and the FTC would be happy to try to facilitate that. One of the things, for example, that he's looked at, and this is a series of screwdrivers, and you can see he actually looked at exactly, it only shows 6, but I believe that there were 10. And so here, tip 20, let me see if I can get that. So tip 20 here, and side B of the screwdriver. This one did not match. This one matched a 23B, and said the screwdriver was at 75 degrees, and it actually was. The algorithm said 80 degrees, but the reality was 75. Most of these, though, were exactly right on. So here, 23B at 40 degrees was the prediction of his algorithm that was based on a large number of acquisitions of looking at screwdriver impressions, and it predicted 23B at 35 degrees. So in general, it was able to not only identify which screwdriver made the impression, but also which side of the screwdriver, and within 5 or 10 degrees, what the angle of that screwdriver impression is, and do so using a reasonably objective algorithmic approach. And that's really interesting from a tool mark examination perspective, to be able to not only say this screwdriver made the mark, and within a certain plus or minus of the degree of attack of the screwdriver in question or other tool mark, but also to be able to say, hey, there's some objective basis for why this particular match was occurring, and some objective basis for how accurate that match is. That's in some ways I think is going to be very valuable for us long term in terms of the validity of the tool mark examination process. And certainly encourage any folks who have a chance to work with Dr. Chumbley to do so. And like I said, the FTC would be happy to try to facilitate that if you would like. Another system that uses focus variation among other approaches is the Scan by Evo Finder, which again is used not in the United States so much, but around the world a lot, in Europe, Egypt, China, and elsewhere. And there is an unnamed county crime lab actually used the Scan by Evo Finder with cross-correlation function algorithm and a reference database built using the Evo Finder only to replace their heritage IBIS when they lost that and were no longer part of the NIBIN network. So they basically built their own system using the Evo Finder, and with very, very solid success. They used the Tolliner's data set, which is a set of 792 Smith & Wesson Model 4006 40 caliber pistols. They did a couple of test fires using some federal ammunition for most of them, and for some of them they used 5 test fires. And then they went to build a reference database for validation. And then they did 49 test fires to see how well that worked. And when they used both breech face and firing pin, they got 49 out of 49 at the #1 hit. Now, you'll see with all of these kinds of systems that when you, and this is not just with optical topography, this is a general issue in firearms examination. When you bury the ammunition, that's when it gets hard. And when they did that, they still, however, got 85% matches at the top hit if they accounted for both the breech face and firing pin impression. That is 4 times better than what the Heritage IBIS system was. That particular laboratory is now a NIBIN site, and report qualitatively that the Evo Finder and the new HD 3D brass track system are comparable to one another. They were able to produce cold hits in a database of over 1,000 firearms in the meantime, though, using Evo Finder. So there are other systems that are viable alternatives, and some for agencies that are non-NIBIN systems that are out there and that can be deployed to do that kind of reference database work. Another county, Orange County, California, did a very similar kind of work, and I understand this is continuing, using what they called OC Bullet, which is their reference database system, using Evo Finder. They, instead of doing the Tollner's study to validate, they used a Brundage barrel test set and came up with very similar kinds of quality metrics with respect to the accuracy of the correlation function that Evo Finder uses, which is basically the NIST algorithm for cross-correlation functions. Again, they were a non-NIBIN jurisdiction, and they've been able to produce 50 hits with the Evo Finder system, which is 10 times more than what they were getting, more than 10 times more than what they were getting from the Heritage NIBIN system back in the day. And they are applying, and they are one of the first counties also, first jurisdictions, to apply optical topography as a complement to the comparison microscope. In particular, they're using it to prioritize when the comparison microscope is used. The comparison microscope is a precious, the time on there and the amount of effort that it takes to do a comparison there is extraordinary. By using the Evo Finder, they're able to find which matches are really inconclusive and which ones are clear matches. And by using the Evo Finder clear matches and only doing the comparison microscope on those, they've been able to prioritize their comparison microscope time appropriately. I hope am I still online, Josh? I hope I'm still online.
Yep, great.
Okay, good. Interferometric microscopy is the next one. And there are several systems. The Sensifar actually uses interferometry as well as other modes as well. There are many other interferometric systems that are available out there commercially, especially outside of the forensic science community. Most of these systems are systems that were developed outside the forensic science community and now are available inside to forensic scientists. And the idea of interferometry is when you have 2 interfering light waves, they will create an interference pattern. So when the green and the black wave interfere, they create the red one. And so by looking at the variations in that interferometric pattern in an interferometric microscope, one set of light is reflected off of the object, the other is reflected off a nice smooth mirror. There's an interference pattern when they are brought back together, and that is used then to recreate the image of the object. The photometric stereo is the last one that we'll refer to. That's the gel site one. I love this picture. This is so photometric stereo was, as you recall, my original discussion was where each facet is like a mirror, and so of a surface is like a mirror. And so as it varies in height or varies in angle, it's going to reflect a little differently in the light. And this actually is it's possible to get very fine detailed images this way. The one drawback is that the photometric stereo microscope varies with respect to the color as well, right? The dark or light. And so they use these gels on top of objects. They get a gel impression of the object and then make the image off of that. And here you can see they use an Oreo cookie to make a gel, and it's actually quite accurate how that works. And again, if you have a chance to go to IPTIS or to listen in to the presentation, Ryan Lillian is going to be talking about the gel site system and how they're developing it. And and here's some of the image data. This is what the system looks like. Here's some of the image data from there, and they have their own algorithm for doing matching as well using the GelSite system. It is not yet available commercially, but they have done a fair amount of research on this. The key to this is that it's demonstrated how interoperable the data can be here. So again, here's some pretty pictures of the system and how here's a gel. You can see where the firing pin is picked up by the gel here. And here again is looking at the NIST standard reference cartridge casing. Just beautiful, beautiful data. And of course, Ryan, of course, downsampled that. It's so good he had to downsample that. But one of the things that's interesting is that they have taken the data from the nanofocus system. That's the basis of the brass tracks, and they've put it into their system, imported it using data exchange algorithms, a data exchange standard, and been able to show that they can come up with the same kind of matching as it would be if it were under an IBIS workstation. In other words, once you get to a certain level of quality and you're using data exchange standards, you can actually be a little bit more technology agnostic here among all of these different systems. And that's a very, very powerful impact on the future of firearms examination for us. And I'll talk about that here in a little bit. The question now is just how good is optical topography? Now, we all, back when I was at NIJ, I was very fortunate we were able to start an examination of this. And we asked the National Academy of Sciences to answer that question. And they actually addressed this issue. Is it possible to even create a national reference database of ballistic images of all new and imported guns? And they said, no, it's not advisable because we just can't get good enough data. But this three-dimensional measurement systems might give you the capability to do that in the future. And at the time, my good friend Robert Thompson, who, if you recall, helped out with the long seminar on this topic out in Phoenix, summed it up very nicely. The dynamics of a bullet going down the barrel of a firearm, the downward movement of a fired cartridge case against the breech face of a Glock pistol or any pistol, or the movement of a screwdriver across a door strike plate, all leave three-dimensional tool marks that can change considerably in a short distance. These features, tool mark angle, ammunition variability, and tool barrel wear are features that an examiner considers during examination, and none can be fully captured in a two-dimensional photograph. In other words, having the three-dimensional data is really a change in how good optical topography can be. So are these systems really good enough now to revisit this whole idea of a reference ballistic imaging database? And Jan de Kruster, who has done a lot of research in this area, actually looked at this and published this in Forensic Science International in 2015. These are our European researchers who concluded even though optical topography is really, really good, there are some basic physics that's going on with respect to firearms and cartridge cases even that make this very, very difficult, especially as you vary ammunition types across within a firearm. So they looked at 592 reference cartridge cases back when they were looking at the Heritage IBIS system. And they compared it to the Evo Finder. So the same system that was used by, say, Orange County and that other county, they actually looked at all of those cases using that new Evo Finder system. And they found that 38% of the time for them, the target cartridge was at the top of the search list, even when there were variations in ammunition type. And that was, for them, twice as good as what they saw with Heritage IBIS back before that. But in the end, their conclusion still holds that the reproducibility is predominantly influenced by the cartridge case and primer hardness, ammunition manufacturer matters, and it still requires a lot of work by an examiner to make most matches. These are not, these tend not to be lights out matches in most cases, and it is advisable to back it up with the work of an examiner. I mentioned how we need to do a better job selling the impact of these types of technology improvements in our work in forensic science. And I'm going to highlight this set of research, and there's actually several papers that Anthony Braga has published on the impact of NIBIN itself. So even though we can't, and there are a lot of reasons also why one might not want to have a database of all guns sold. But that said, a database of all crime guns can be extraordinarily valuable. And the impact of NIBIN in its current form, and I think in its future form could be even greater, was demonstrated by Braga's research. Boston put in 2,400 bullets and 12,700 casings into their IBIS system from 1995 to 2003, recorded 412 hits. And what's really interesting, before that, they got 9 cold hits a year. And that was usually because of a really, really smart firearms examiners. Like, I remember there was a firearm that was captured back, last May, and it was using this. It was from a similar type gun, and I remember that the firing pin was a little oblong, and they would make cold hits that way. And God bless them, they were able to do it. But they went from 9 to many, many more than that. About 50 or so a year, and I assume many, many more. Braga actually looked more particularly at 104 of those hits out of those 412. Of those hits that occurred, 72 of them involved cases where shots were fired and 17 homicides. So the others might have been where firearms were seized as part of another crime or something like that. Within those 104 hits, 59% of the people who were identified were convicted felons, 42% gang members. On average, each individual had 10 arraignments on average for prior offenses, including 2/3 with a violent offense, and 2/3 had been to jail or prison. And fully 3/4 of the hits led to a conviction for a new gun crime, and 87% of those were incarcerated. For the pre-IBIS time, that was less than half, or roughly half of that figure. So that's an incredible. It isn't just that you're getting more hits; you're also getting hits against really, really bad guys, and you're getting convictions too. So that's extraordinary. And he looked at more recently, here in just 2015, at this whole issue of ballistic imaging, and in particular this whole idea of how well bullets can be you can get bullet hits, as well as looking at how well NIBID agencies were entering evidence. And the fact is that I can see 5 years ago, 10 years ago, before the advent of brass tracks, there were a lot of agencies that were not putting a lot of evidence into NIBIN. But anybody who has a brass track system who isn't using it to its fullest extent and really aggressively putting in those that evidence is really missing out on the full capability that NIBIN can offer these days. And further, it's worth it to be looking at bullets as well. The bullet track system has allowed Boston to, after they adopted it in 2009, to go from about 1 bullet hit per year in the 13 years before that to 4 and 5 in 2009 and 2010 under Braga, and that was part of Braga's research study. And I encourage you all to take a look at his stuff. And he really, and to sum it up, the technology needs to be accompanied by an organizational commitment to image and analyze all recovered gun crime evidence in a comprehensive manner. Law enforcement agencies also need to ensure that linked information gets to the appropriate criminal investigators, and that these investigators follow up on all investigative leads. If you are not a firearms examiner or in the crime laboratory, if you're in a police department, if you are somebody who is in whose job is to investigate crime, or you're a police chief, please, if there's nothing else you take away from this presentation, please take that away. This technology allows the firearms examiner to do an awful lot more for you, and please and actually solve cases. This is an extraordinarily important takeaway for those who are outside of the forensic science community but customers of it. The New Jersey State Police have done a great job with this, and they used to take 10 months to 2 years to put a crime gun into NIBIN. They decided they were going to get that down to days. Their real-time crime center serving 800 agencies made this a priority, and they have, since doing this, have gathered over 1,000 hits, NIBIN hits in Newark alone. They have found that executive leadership can enable more efficient use of firearms identification data through the development of processes that prioritize evidence and eliminate the policy choke points. And they are not the only ones. It's seen across the country. Colorado, Denver in particular, has done this, and many, many other jurisdictions. So I hope everybody notes that and really understands the impact that they could have in this area. There are still challenges for the next level of the use of this type of technology. First of all, as DIST themselves will say, their bullet and casing standards aren't ideal for the assessing of these systems and for the validation of them in the laboratory. For example, with respect to understanding lateral resolution and slope and stitching, all of these systems have limitations when you are looking at steep slopes within an image. And of course, there's an awful lot of steep slopes in cartridge case and bullet examination. A lot of them can do those slopes, but there are limitations there, and those need to be understood and quantified as part of the validation process. Training is also an issue. There's a whole generation of folks out there that has been trained to use the comparison microscope. We're not talking about getting rid of the comparison microscope, at least not yet. But there's certainly not a lot of training in how to use these optical topography systems. And that's something that we as a field need to work on. One of the things that we need to also understand, and that is that we really want to try to push the community of the commercial community to allow for open data interchange standards. These data standards can be enormously beneficial to us. As I mentioned before, Cadre has demonstrated that data that's captured within a standard interchange format can be interoperable across these systems. And there is a group that has developed a particular data set that's X3P under the Open FMC consortium to exchange this type of optical topography data. The Open FMC includes header information, metadata, the actual profile data, as well as some checksum data to check on the integrity of the data of the file set. And if every type of system could talk in X3P, then the commercial market can open up a great deal more. And it is my understanding, I do not work for ATF, and you heard the disclaimer at the front of this presentation, but it is my understanding that this is the direction that ATF is going with NIBIN, and that is that they want to see a much wider variety of systems to be able to use the NIBIN network and then talk in an interchange format like X3P. So therefore, you would be able to use any of several different kinds of optical topography systems and store the data in X3P, and it would be interchangeable across jurisdictions. And that kind of ability to use a wider variety of technologies and commercial systems will open up. I think will make it much more cost effective for more agencies to participate in the NIBIN system and really squeeze a lot more value out of the reference databasing that's possible using optical topography. I'll close with just a short discussion from the perspective of the reliability of forensic methods, which it's almost required when you do a talk like this to talk about the 2009 National Academy's report on forensic science, which laid out this issue and included talking to some extent about firearms examination. One thing that we should keep in mind is that optical topography provides an inherently quantitative method for tool mark examination and should, not today, because the statisticians are still arguing over it, should provide a basis for statistical evaluation for firearms and tool mark examiners, and give us a quantitative way of characterizing comparisons. And again, this is my view. Merely doing something like consecutive matching stria does not mean that you have a quantitative comparison, because we don't really know from a population statistics perspective what the CMS really means. How unique is it to say you have 3 or 4 consecutive matching stria, for example? We really don't know the answer to that question in almost any case. One day, I believe, again, this is John's opinion, every laboratory will use optical topography to perform all tomark examinations. In the meantime, we know that examiners are using the comparison microscope, and labs know how to validate these methods. They know where the current practice is not leading to false positives. There's very little evidence that we're getting false positives. I think the issue is we're not getting enough true positives. I think there's a lot more matches out there that we could be getting, both at the reference database side, but also in the examination, in the examiner side, by using optical topography more extensively. And I don't know, Josh, should I try to wrap it up, because I am at the top of the hour. There's one of the things I want to just point out, and I'll talk about it maybe just very quickly, and that is the understanding of the probative value of comparisons. And I think understanding this in more detail is well worth the time of the average forensic scientist, and I encourage you to think through the idea of what it means to say something has probative value, because it depends on things like the variability. And variability can mean a variety of things. It can be natural, that is, within the object in question, the evidence in question. It can be analytical, that is, which filters, or the operator. We talk about human factors. Every operator is a human being, and you're going to have differences in how you analyze things. There might be differences in instruments as well, and also in the assumptions and statistical methods that are used to characterize these if you do a statistical interpretation. And each one of those is very heavily influenced by the assumptions involved. We have a plenary session at IPTIS that's actually going to be looking at this issue in great detail. So if you have a chance to listen in, at least, on the plenary session on statistics at IPTIS, you can really learn an awful lot more about what it means to say we're going to be making assumptions that lead to particular characterizations of forensic examinations on a statistical basis. And I obviously don't have time to really go into that in great detail here, but it certainly involves looking at the sources of variability, and this is just a small list, including things as simple as the geometry of the sensor relative to the object being sensed, and the material properties of the object, and so on, and noting that we thought rigorously about what the error sources are, especially when we look at new technology. And those error sources can be about the technology, but it can also be about the human, as I've said. We're actually in the FTCOE creating a source book on human factors, and I hope that we'll be able to help folks understand how cognitive psychology can be used to help us make better comparisons and do it in an efficient and good and useful way. So I'm going to just skip over the rest of this. This is a table from the landscape report. The landscape report this is just one small, there's actually dozens and dozens of these parameters that the landscape report looks at, and gives you some sample questions you can ask about different kinds of optical topography instruments. And so this is from that report, and a snapshot of that one portion of that table. It also looks at the very specific instruments from each manufacturer. We ask the manufacturers themselves to participate and give us their data on what kind of microscope they have, how they manage data, what is their reported resolution, and all 9 yards. All of that is in the landscape report. I encourage you to take a look at that. So in summary, optical topography is a useful complement to the comparison microscope. Can be used to exclude or clarify the basis for a comparison decision, and is definitely useful for reference databasing, and well worth the investment of time and resources in expanding its use for in the reference database side, using the current NIBIN system, or whatever it is whatever direction ATF ends up going. I'm John Morgan. This is my contact information. The other thing I will ask you to do is if you haven't seen my podcast, I do a podcast called Just Science. We've had over 30 episodes thus far. Just Science is a podcast for forensic science professionals, for people like yourself. So if you want to learn more, not only about your own field, but about other fields within forensic science, you want to learn about the latest trends in research and practice and leadership and much, much else, or just learn about some of the legends of forensic science that we've had the advantage to be able to use their work of, please go on to your local podcast tool. It's available on all of the major ones on Apple and Android, and listen to the Just Science podcast and spread the word that whether you're a forensic scientist yourself or a student or just somebody who works with forensic scientists or just curious about it, Just Science is a great way to get educated, and happy to have you be one of our listeners. So that's that. Josh, do we have some questions?
We definitely do. The first one is more of a comment that came in from Todd Weller. He just wanted to make mention that the Cadre forensic system is commercially available now and has actually been validated by the FBI for use in virtual microscopy.
Oh, fantastic. Thank you, Todd. I did not know that's new information. And I also want to
right.
clarify for everyone, I know that I see one comment over here that the optical topography does not replace what is already being done by practitioners throughout the discipline. And that's definitely the case. It is definitely a complement to what else is going on, especially with respect to it being used as a complement to the comparison microscope.
All right. Our first question is from Laura Draga. She's asking, is the 2-minute scan for a bullet or is it for a cartridge case?
In that case, that was Derek McLaren doing a 2-minute scan of a bullet. But you should assume that you're going to have those kinds of scan times, either in just that general order of magnitude for either a cartridge casing or a bullet, to be able to capture all of the data necessary.
All right. Next question we have is from Jessica Wade. Can GelSight give the topography of firing pin impressions as well?
Yeah, in fact, if you saw one of the slides, actually showed a beautiful picture of a firing pin impression using the GelSight system.
All right. Next question we have is from Bishoy Dawood. He's asking, how do you compare two images and decide the match? Are you assessing the matching virtually or are you using an algorithm? And if so, how do you assess the actual quality of the image if you're viewing it virtually?
Those are excellent questions. And I can tell you that I have been in conversation with, we had a working group on that developed the landscape report on optical topography of folks from this country and around the world who participated with us and asked those very questions. And I don't think it's possible to answer those questions in a rigorous way today. I think the hope is that one day you'll be able to assess the match using an algorithm. That is, that you would be able to have two images side by side. The algorithm would be able to give you an assessment and give you a number with respect to the uniqueness, although I suspect we will always have the need to have the human examiner in the loop to be able to judge that. Because that's even true now, for example, for DNA analysis, where the underlying data is much simpler, and in particular for like mixture interpretation. If you don't have a human examiner in the loop judging what that DNA mixture interpretation software is telling you, then you're going to get it wrong 99 times out of 100. And so it's very important to have a human examiner in the loop being on top of what the algorithm is telling you. At this point in time, what I would say is that the systems are very, very useful for use as a reference database and to complement the comparison microscope, and therefore you're still looking at using this data in the same way as you would look at a comparison microscope image. You're doing a qualitative examination based on the judgment of a human examiner.
All right. Next question we have, we might need a little clarification from Ernest. It was in regards to slide 34, and he was asking about polygonal rifling too.
Yeah, so political, yeah, that's obviously a much more difficult kind of set of comparisons to do when you have polygonal rifling that is done in the manufacturing process of a barrel. There have been folks who have looked at and done some comparisons using optical topography of polygonal rifles, polygonally rifled barrels. That's quite a mouthful, and it does even broader than just the polygonal rifling issue. I think in general, manufacturing methods have, as you might imagine, been improving with respect to firearms. And there are some challenges more broadly with respect to being able to distinguish the consecutively manufactured firearms. These studies looking at consecutively manufactured barrels, I think, are very, very important and well worth examining because traditional methods are going to be a challenge to be able to continue to apply them. We'll need to have the superior data that we can get from the optical topography systems in order to be able to make these comparisons. So whether it be with respect to polygonal rifling or other aspects of the manufacture of barrels.
All right, we've got time for just a few more questions. Next one again is from Todd Weller. He's asking, in the South Dakota study of match scores, what scoring algorithms were used or studied?
He actually looked at match scores not only in firearms examination but also in fingerprints. So he looked at match scores from the APHIS systems, and which APHIS systems I do not know off the top of my head, but he also looked at match scores from the IBIS system. He did not look at match scores from one of the other systems, what are called like the congruent matching systems and things like that. But he did look at the match scores from IBIS systems, and what he found is that they in terms of their correlation with respect to the actual likelihood that they were matching, they were a good characterization of the statistical likelihood of a match. Sometimes they overestimated, and sometimes they underestimated, and sometimes it was radically different from a nice straight line match. Cedric is talking at the IPTIS forum. It is the plenary session on Wednesday morning that he will be talking to that. He has also presented that data elsewise. He has an active NIJ research project. We will be asking Cedric to present it, I'm sure, from FTCOE and some of the other kinds of venues as well. But yeah, he was looking at match scores from APHIS systems and from IBIS. And I'm sure if he were here, he would say in his very sanguine way that he does not believe that other scoring systems would behave differently, that it is inherent to match scores that they would behave in that way.
All right, we've got two left that we can handle for today, then we're going to have to wrap things up. Rachel Bolton King is asking which systems can currently export ballistics data in the X3P?
I think most of them can. The landscape study table actually has a particular row looking at X3P. So I suggest you refer to that to make sure you get good data, as opposed to, I don't want to tell you off the top of my head.
All right.
I think I mentioned the plenary session. So that, again, you can look over here to the right. I don't know whether it goes across here, but it's sort of where the green arrow is. IPTIS 2018, you can do the virtual registration, and it is Wednesday morning plenary session that you should be paying attention to specifically.
All right. Our last, we have a last kind of question and comment. When you were discussing the algorithms in the future, Nancy Burke Bradley had a comment saying the human element is always a plus, and then Jessica weighed in saying, but isn't the point that skeptics want an algorithm to say, yes, this is an ID, without a human actually having to make that conclusion?
Right. Yeah. So I think there's a decision to be made from a policy basis here. So there's, I think, a set of decisions that you're going to make based on what you might need to go into court with versus what you might use to inform an investigative lead. So, for example, I don't believe New Jersey State Police is turning around cases in days. They are not taking those systems, those matches they're getting off of NIBIN, and doing full-up comparison microscope matches there. Instead, they're saying here is an investigative lead that is coming off of a match score, and then they're using that at the appropriate time to do a forensic examination to prioritize forensic examinations. There are those who would like to eliminate the human from the system. I am not one of those people, and I don't think anyone who is reasonable would even want to do that. I don't think that's part of the deal here. And the data in this particular instance, because there's some interesting physics here, I think one fact is that people outside the firearms examination community don't realize is there's enough variation even from test fire to test fire, so that it's what matches that matters, not what doesn't match between two comparisons. And when you're looking at firearms examination, that implies to me that the judgment of a human with respect to evaluating this data is always going to be important. But having this to not only complement the human examiner, but also give you a quantitative characterization of the statistics of a match is extraordinarily valuable. And that's really some of the power that I think we'll have long-term out of optical topography.
All right. Thank you so much, Dr. Morgan. We're going to go ahead and switch over to our closing for today. Before we do you have any closing words that you would like to leave our audience with?
I'll just thank you for everybody's time, and tune into Just Science.
All right, thank you so much, Dr. Morgan. Before we do get into our closing, we do have quite a few references, websites, and files for you to access on the left-hand side of your screen. As throughout the whole presentation, we do have the web links there for the study that Dr. Morgan was discussing today. We do have IPTES 2008, where he was discussing the plenary sessions. So make sure to go there and register for the online version so you can see all of the live presentations during IPTES. We also have our forensic COE website there, so you can check out all of our courses and reports, studies, and then as mentioned, there is our Just Science podcast as the last web link there. In the bottom left-hand corner, very bottom, we have our file share pod where you can download a PDF version of today's slides directly. So for everyone that was interested in downloading a copy of today's slides, please go ahead and click on the title of that file, and then the download files button will highlight at the very bottom of your screen, and you can download that directly from today's webinar before you leave. Again, we would like to thank Dr. John Morgan for his presentation today, for taking the time out to deliver his information to our audience, and obviously we would like to thank all of our audience members for joining us today. These webinars would definitely not be possible without your attendance and your support for our program. Before you leave today's webinar, we would like to ask you to participate in our short survey that we always have. You'll find it there in the center of your screen. Simply click on the word "Here," and it will open up a new window for you. Your feedback on our webinars is vital information that we always use to make sure we provide you the best webinar experience, and also adjust any content and the way we disseminate that content to you. So please take a few moments to complete that survey before you leave. We definitely appreciate it. We did record today's webinar, so it will be available as an archival version within the next 24 to 48 hours. So please make sure you check back on our website, and you'll be able to register for and access today's recording for your reference, as well as any colleagues that might have missed out on today's presentation. Again, thank you, Dr. Morgan. Thank you to all of our participants for joining. We hope everyone has a great afternoon. Remember to download all the materials that we have there for you, and check us out for our next webinar. All right, guys, thanks. Have a great day.